Yeah, hello. And welcome to my talk on artificial intelligence, or more like artificial stupidity. And what I'll be doing today is I want to tell you a couple of stories, about data, about AI, about machine learning. And some of these stories are success stories, but some of them are not, and some of them are failures. And particular into those, I want to dig a little bit deeper and see why they failed, and then propose some ideas why what we can do in the future to prevent that from happening. And when I say I talk about stories, let me talk about one of the greatest storytellers that we have, which is Douglas Adams. And the Douglas Adams has written this book, and I'm sure some of you have read that, The Hitchhiker's Guide to the Galaxy. It's quite popular, especially among us techies, and it has introduced a couple of memes that 42 is the answer to the question of life, the universe, and everything, and that we should not panic. But it also has introduced another thing, and Douglas Adams is calling this thing that I'm talking about the Babel Fish. And this Babel fish is this fictitious fish that he describes that lives somewhere in the universe, and it has this fantastic feature that it's a tiny yellow fish, and you can put that into your ear. And what this fish does is it listens to the brain waves of all the organisms around you, and whenever people around you speak in whatever language, in whatever alien language they want to speak in, this fish translates it into a language that you understand directly into your ear. So you put the fish in your ear and you can understand everything. And that is, I mean, Douglas Adams is was a very creative person. That is obviously fictitious, and this fish doesn't exist, and it's a crazy idea, actually, this fish. And it's so crazy that only Douglas Adams could have thought of that, right? It's never going to be real. But let me show you something else. Hallo und herzlich willkommen zu meinem Vortrag über künstliche Intelligenz. So what we see here is that even though this crazy fish that I described doesn't exist, but machine learning applied correctly nowadays is already helping us translating voice in real time. I mean, admittedly, it's not as cool as having something stuck in your ear and you still have to read it. I mean, I could click this button and it would read it out loud, but we still have this website, and it's not as cool as having this fish stuck in your ear. But there's actually more to it, because Google also is selling these headphones nowadays, and these headphones, these Pixel Buds, are more or less like this fish. You can put them in your ear, and Google Translate, the website that I just used, and the app on the phone is then translating something that someone else is saying in a different language, and these earbuds are then replaying that in the language that you understand. So in a way, you stick something in your ear, someone else says something in a different language, and all of a sudden, magically, you understand that. So this very fictitious, crazy idea that Douglas Adams described is more or less being made possible nowadays with machine learning. And that's like one of these stories where I think that machine learning actually does something really cool and something really useful. But there's one example that I like even more, and it's the example of cancer cell recognition on image data. So taking pictures, and you can see that here in the on the top. They're taking pictures of cells, of human body cells, and then deciding whether it is a cancerous cell or not. It's typically done by trained professionals, by medical doctors who have experience in that field and who know exactly what they need to look out for, and what a cancerous cell looks like. But for a couple of years now, people have been training machine learning models on this particular task as well. And in fact, for a couple of years now, for breast cancer, machine learning models have been proven to be more accurate than medical trained professional doctors whose job is it to detect cancer cells. And that has been going on for a couple of years for breast cancer. And I think last year, Google released a machine learning model that is better at detecting lung cancer. Like you the same picture that you take of these cells and you would give it to a doctor, you give it to a machine learning model. The machine learning model has a higher accuracy than the doctor, and that's literally life-changing feature that we get from the machine learning models. But the title of this talk would not be Artificial Stupidity. I mean, it's kind of I'm kind of clickbaity so that you all come and watch my talk, and looks like it worked. Otherwise, you wouldn't be here. But there's also something behind it, and the reason is that it often does fail. And when we look here to the right side, there's this fellow tweeting to Indigo, which is an Indian airline, and he's saying that he is thanking the airline for flying him to Kolkata while sending his baggage to Hyderabad. And we as humans, we clearly know, okay, there's some sarcasm. That guy is not really happy. But and I assume there's some kind of AI, some kind of chatbot behind this Twitter, because the reply from the airline is, we're glad to hear that. So obviously, that is not the appropriate response, right? But the AI didn't pick up what the real meaning of the message was. And in the middle, we see something similar. A PayPal customer said, "Hey, I got scammed," and for some reason, the machine that is answering this comment is saying, "Hey, that's great. There's nothing great about being scammed," and everyone knows that. It's just a machine not realizing what's going on here. And on the left side, we also see another example where machine learning fails. And these are simple examples, but there's also and might not even be that painful. I mean, some chatbot on Twitter messing things up doesn't really hurt you that much, right? But there are other cases, and my favorite example is this. And if you speak Mandarin, you might be able to figure out what's going on. For everyone else, I'll give a little bit of a background. So there are, in a couple of Chinese cities nowadays, there are cameras installed at zebra crossings. And basically, what these cameras do is they watch the zebra crossing, and if someone is crossing the street, a pedestrian, while the pedestrian actually has red light, then the camera takes a picture of that person. And what you see here, there's a gigantic screen next to it, zooms in and shows that picture of that person. Hey, this person just jaywalked. And in fact, it's not just image recognition, identifying, hey, there is a person. It's also face recognition to find out who that person is. Now, if you look closely at this example, you can see there's not really a person crossing the zebra crossing, right? There's a bus. There's a bus with a face printed on the side of it. There's some advertisement. In fact, I know the person we see here is the CEO of that company, and they're advertising with her. And the bus having green light is driving by, and the camera picks up this printed face and thinks, hey, there's a person. And is shaming the person here on the big screen, saying, hey, this person just crossed the road, just jaywalked while the light was red. Now, this person got a text notification a couple of seconds later. Hey, we saw you crossing the street, this crossing there and there. And the person was like, how does that make sense? I'm in a different city right now. How can you see me crossing the street in this other city? And that's obviously an example where this machine learning and the image recognition, as well as the facial recognition, is both based on machine learning, failed pretty badly. And I think in this case, it was not the case. But in other cities and other systems for pedestrian crossing, do not stop at face recognition and identifying who that person is, but they actually have a link to the WeChat Pay account, so like the bank account, the wallet, if you will. And they're actually deducting the fine for crossing the street immediately, like within seconds. Like the machine learning model picks up, hey, this face, this just crossed the street, looking up who does this face belong to, what's the bank account, what's the phone number, what's the WeChat Pay account ID, and then deducting the money immediately. So, and that is something I mentioned. The Twitter bot might not be that much damage. In these cases, there can actually be a big damage be caused by this error of this machine learning model. And if you think about further, like, I mean, even maybe a fee for crossing the street is not that high, but there are other things, right? Like, imagine you go to jail because a machine learning model decides to wrongly. So that would be pretty bad. So I mentioned a lot machine learning and AI, and I think, at least for this talk, it's important to have a common understanding of what these terms really mean. And there's this, at least for the artificial intelligence, there's this definition that I really like. It comes from the Oxford Dictionary, which is also used if you type Google define artificial intelligence, this is what you get. And the definition reads that artificial intelligence is the theory and the development of computer systems able to perform tasks normally requiring human intelligence. Now, the important part to note here is this is not talking about a technical implementation. It's talking about the concept of something done by a computer that you would usually think requires human intelligence. I'll give you an example where it becomes clear that the technical implementation is not relevant. It's a chess program. If you think about it, a computer that can play chess, you would think there's like, I mean, if it were a person, that person needs to have some kind of intelligence, and our computer can do that, so that matches this definition, right? But if you implement it on like a software level, it could be as simple as looking at the state of the board and just brute forcing all the possible moves and all the possible subsequent moves. Just all of them. I mean, there are a lot, but just all of them, and then pick out a set of moves that leads to the desired outcome, which is winning the game. So there are a couple of ifs, a couple of loops, but there's no crazy, sophisticated software implementation behind it. Right? It's relatively simple. Yet artificial intelligence is everyone talking about it. It's very cool. It's a big marketing term nowadays, if you ask me. Machine learning is where it becomes really interesting, because machine learning is where the software developer is not the one designing the algorithm, which at the end makes the decision. It is the data. You train a model, you put data in, you say, hey, this is the data I give you, and this is what I expect as an outcome. You do that a couple of times, and then you hope that your model has generalized the behavior. And if you give new input data, it predicts correctly, or it gives the correct output. And that's just pretty cool. And then there are neural networks, which is a type of machine learning built modeled around natural or biological brains. And then there's deep learning, which is just like neural networks with a lot of layers. I'll get to that in a second, right? And I think that's at least for this talk important to understand. Now I've mentioned neural networks and I've mentioned machine learning, and one of the issues, or one of the big issues that I see with the widespread deployment of machine learning nowadays, and the examples kind of hint towards that, get a little bit explained here. And this is a very simplified view. It says deep neural network is actually not that deep. Production models nowadays can have 50 or even 100 or even hundreds of different layers and thousands of neurons, thousands of nodes per layer. So this is actually relatively simple, but we can already see all these nodes are connected, and all these connections they're sending information somehow, like they're sending some kind of value, like it doesn't really matter what it is, but there's some kind of connection between. And if we now look at this with our human eyes and try to figure out what's going on here, because there's so many connections, it's virtually impossible to see where these connections go. And if you think about on the left side, I put in some data, and on the right side, there's some output. It's impossible to comprehend why this input data now caused this output. And as I mentioned in real life, these are 100 times bigger in real life. For humans, it's basically impossible to figure out why this neural network behaved in the way that it behaved. And that is one of the big issues that caused at least some of the example failures that I showed before. It's basically a black box, and I have no way of knowing how this model will actually behave. And that is, I mentioned that is one of the big issues, the black box behavior of machine learning models, and that we don't really know how it behaves if we give in new data. Probably, the bus with the person on it, that machine learning model was not trained with bus pictures. So that is, or bus pictures with a person on it. So that is where we didn't know how it will behave, and nobody tested it, and then it behaved wrongly. And we had no way of knowing by just looking at the model itself. Right, so that is one big issue, the black box behavior. Let me talk about the second big issue that I want to address today. And I'll give you another story. And this story is about the city of Boston in 2011. The city of Boston had a problem. They had potholes. All over the city, there were potholes, and they wanted to fix that. And they did what everyone did in 2011. They wrote an app. So they had an app for it. And this app, I mean, actually quite smart. The app worked in the way that you would drive, if you were a citizen of the city of Boston, you were driving around, and when you were in your car, you would take your phone, open the app, put the phone on your passenger seat, and drive around. And when you were driving across a pothole, there would be some vibration. The phone would pick up the vibration and then take the GPS coordinates of this particular spot and send it to the server. And the city of Boston then would have a list of, look, all these GPS coordinates and all their vibrations, there must be potholes. Pretty smart, actually, what I think. And then they did that for some time. And then they found out that all these potholes that were reported were only in the high cost of living areas, only where the rich people were living. And now, if you think about that, does it make sense that there are only potholes in high cost of living areas? I mean, they should be more or less evenly distributed across the city, right? I mean, if anything, then there would be less potholes because there's more money to get fixed in these areas. So it doesn't really make sense. And the reason for this discrepancy between what you expect and what the data showed is because 2011 was different from now. Nowadays, everyone has a smartphone, right? Like every 5-year-old is watching TikTok videos on it. 2011, smartphones were relatively new, especially ones where you could install apps, were relatively new and still relatively expensive. Not everyone had one, and only the rich people had one. So that's why only the rich people would put them on their driver's seat, and they would only mostly drive in their rich people areas. So that's why they only had data about these areas. And now the very important thing to note here is there's no machine learning involved. There's no machine learning, or if you will, artificial intelligence. There's nothing special about. They were just collecting data, but the data itself was wrong. And that is the second big issue that I see with the nowadays widespread deployment of artificial intelligence. That the data is skewed, and we use it and we rely on it. And let me show you something. Some of you might remember this because it got popular some time ago. If I write this sentence, he is a nurse and she is a doctor. And in English, and it's very obvious, like I'm saying he is a nurse, like the male is a nurse, and she, the female, is a doctor. And I translate this into Malay, and Malay has this neat little feature that, interesting, that it does not have gender-specific pronouns, like we have he and she here in English. In Malay, I'm not going to pronounce it, but I think the first word here is the pronoun. It's the same for he and for she. So there's no differentiation, which is interesting, right? Now, if we translate it from English into Malay, we lose the gender information. And now if I click this button in the middle, it translates back the Malay back to English. And note that I have specifically said he is a nurse and she is a doctor. If I translate it back, all of a sudden the retranslation reads she is a nurse and he is a doctor. So they switched genders for some reason. I have a gendered pronouns translated into a non-gendered pronoun language, and then back, and all of a sudden the genders are switched. So, and the reason for that is, even though there is machine learning involved here, multiple systems probably, and I called it out as a great example actually, because I really, me as a non-Singaporean living in Singapore, I actually need that quite a bit. What happened here is that the way these translation, and it's not just Google Translate, right? It's like all the other services as well that do translations. And they basically, these models basically learn from text. Like you give them a lot of text, like text in English and text in Malay, and then the text is the same, it's just different, and then it learns, this means that in that other language, and this means that in this other language, and it basically learns by heart how to translate things from one to the other language. And now the thing is, all these text, like historically speaking, most of the doctors were male, and most of the text said he is a doctor, and most of the nurses were female, and it said she is a nurse. Now, nowadays we know it doesn't really, like there's no reason why she can't be a doctor and he can't be a nurse, but historically speaking, lots of the texts did have this connotation, and this is what the model picked up, and this is what the model now shows us. And that's where, and that's where, again, the data actually screwed us up, not the machine learning or the black box behavior of the machine learning. And Google, I mentioned it got popular a couple of years ago, where it was for the Turkish language actually, where people noticed that and complained about it, and then the solution was, look, we have this special case, and we give you special information. Hey, in this case, it might not be correct, but that is manual work. And that's not gonna be applicable to all the specific cases for the model. So that's extra effort. Another example where data messed up big time is Tay. Some of you might remember this. Tay is a you can say like a conversation bot that got developed by Microsoft. And they sent it to. They basically it knew how to phrase, how to send tweets, and then the idea was that it learns from the people on Twitter how to have a conversation. Now, if you think about it, if you want to teach someone how to have a conversation like a human, maybe choosing conversations on the internet is not the best idea. If you look at the conversations that typically happen there, and maybe Twitter is particularly bad. Anyway, what happened was people figured out, okay, I can say things, and this model will pick up, and based on the data it learns, it will then create their own identity and speak in a certain way. And there's obviously a lot of people abused that and sent horrible messages and basically made Tay sexist and racist Twitter bot. Right. There's the one thing that I really like is that one of these examples where someone says, "Hey, you are stupid," and Tay correctly says, "Hey, I only learn from you, and if you're stupid, then if I'm stupid, then it's because of what you taught me," and that is basically what happened. Right, but then a Twitter bot again, maybe not the most impactful thing. There are other things like the Compass system. If you are in the US, you might have heard about this. This is a system that is used by judges in the US, and basically what it does is someone commits a criminal, that person then gets asked like 213-ish questions, and based on this questionnaire, there's this system that predicts how likely it is that this person commits a crime again. Basically, it gives like an indication to the judge, hey, very likely or not so likely. And then the judge uses or can use this information to determine the amount of bail, or even to determine the amount of the prison sentence. And obviously, I'm going to tell you now how horrible that works out. There was ProPublica that did an analysis of this, and what they found out is that there are basically two ways how the system can be wrong. The first one is they say a person will recommit a crime, but then the person does not actually recommit a crime. And the other way is like it's a false positive and a false negative. And the other way is the system says, I don't think that person will commit a crime again, but then the person does. So what ProPublica did, they looked at these predictions, and 2 years after this prediction, and looked at the particular people and whether they did recommit a crime or not. And what they found was that for African Americans, 44.9, almost 45% were labeled a higher risk in terms of, hey, they will probably recommit, but they don't actually do that. But they did not do that. And the same thing for white people was only 23%. And then the vice versa, being labeled a lower risk, but that actually do commit a crime again, was almost 50% for the white people, but only 28% for African Americans. So you can clearly see there's a bias based on the skin color. There's a racial bias in this system. And the interesting part is actually that none of the questions clearly are, like, none of the questions ask for the skin color, for example. But there are some quasi-identifiers. They figured it out somehow. And this system is still being used, and I think that is a relatively impactful system. Another example is, autonomous driving cars. They will take over our streets at some point, a couple of years, maybe not 5, maybe not 10, but 20, 30 years, there will be a significant amount of autonomous driving cars, right? And there was a study that found out that these autonomous driving cars, basically, they have a lot of sensors, right? A lot of them are cameras. Some systems are only cameras. And what these cameras do is they use some kind of machine learning, some image recognition, object detection, and basically they figure out, okay, there's a pedestrian, and then telling the car to react in a certain way, like braking or like driving around, something that does not include killing, like driving into pedestrians, right? You want to prevent accidents from happening, right? And now the study found out that if you are a dark-skinned pedestrian, it's less likely to be detected as a pedestrian. So if you think about this, we have a million or a billion cars, and they will have to prevent accidents all the time, like drive around people. And if you're dark-skinned, then the chances that you are being detected as a pedestrian is lower. And that means the chance of getting into an accident and potentially getting killed by this autonomous driving car is higher. So there's a racial bias that will end up killing people because of their skin color. And that is what we're building currently. That is what's going on. And I think that is a horrifying idea. And I remember when I was a child and my friends did something and I couldn't do it, and my mom said, I told my mom I want that. And my mom said, just because your friends do it doesn't mean you can do it. But that's exactly how machine learning works. And now you're looking at me and say, Aiko, you're telling us, oh, machine learning everywhere, everything is horrible, the world is on fire, what can we do? I tell you what we can do. What we need is, we need to address these two issues, right? The black box behavior and the data that might be biased, social biased. And for the black box behavior, there's already the industry is already moving towards explainability as a first-class model selection criteria. You want to understand why a model behaves in a certain way. That is already in the minds of people developing these models. And I'll give you an example. Now here on the bottom, you can see it's the method is called deconvolution. It basically means for convolutional deep neural networks, you can see what each layer actually identifies, like edges or like bigger features or even bigger features. So that is something that we do. What we want to do in general is we want to move away from this typical machine learning approach where you just have data, you throw it into a model, and then you take the outcome. We need to move into a direction where we have the data, throw it into a model, interpret the behavior, have human inspection, and then use our understanding of how the model behaved, whether it was good or bad, and feed that in, change some parameters, train it again, and actually improve it. And one way to identify to understand how machine learning models work is this LIME. And this is a tool that I really like, and I'll give you a quick rundown how that works. It's actually really cool, and it's really simple. And in this example, there's this picture of a tree frog, and it got identified by a machine learning model as a tree frog, right, with 0.45 accuracy. And what LIME does is it's taking the information, hey, this is the input and this is the predicted output. What if I take away some of the input And we can see that here in the middle on the top. I take away some of the input, I make it gray, and let's see if the model still predicts it's a tree frog. And we can see if in the middle here in the top, this strap removed, it still identifies the tree frog. Then that means that the data that we still have is very relevant for a tree frog, and the data that we threw out is not relevant, isn't at all for the tree frog. And we can see that here in the middle, we threw out some data, and now the machine learning model has no idea what it is anymore. So that is a clear identifier that we threw out too much data. So basically what we do is we throw out data, see how it behaves. If it's close to the original prediction, then the data we threw out didn't matter. And that's how we can figure out what actually matters in this particular model and why it behaves in a certain way. Another thing that we would want to address is having more diverse teams. I mean, there's a topic that is in our industry for quite a while now. And that is a problem that we need to address. And for machine learning models, that is the case as well. Where you remember the autonomous driving cars, right? If that would have been a team that developed this system, that would have had dark-skinned teammates, maybe that would have been tested for that case. Maybe they would have found out, hey, okay, it only works for these people, but not for the other. We need to fix it. So having a more diverse team actually gives you a different perspective and gives you a broader perspective to actually address a couple of things that you wouldn't do if everyone's just the same and has the same perspective. Then there's one thing that I would recommend having a look at before starting, like a data-centric project, which is a data ethics canvas. Basically guidelines that you want to ask, questions that you want to ask yourself. Hey, who is this data for? What are the limitations? Like, who am I sharing this data with? And a couple of questions, like when you start a project, look at these, ask yourself, okay, what am I doing here? And understand the data that you have. Another way to understand the data that you have is Google Facets. It's like this nice visualization. You can just take your data and dump it in there, and it gives you a ton of visualizations where you can immediately see, okay, look, we have this data about users, and looks like we have only 20% female in our data, so they're clearly underrepresented. And whatever we do with this data would be skewed towards other gender. And a lot of things that it makes it easily identifiable. Okay, our data set is some more messed up, and we need to fix that before we do work further with that. That being said, thank you very much for your attention. I hope I could give you some ideas of the two big problems that I see with the artificial intelligence that we deploy nowadays. But I also hope I could give you some ideas on how we can address that and how it partly is already addressed nowadays. And if you have any questions, let me know now. Or if you Google my name, you can just, it's a relatively unique name, you will find me, and then you can contact me there and ask me there. Thanks a lot.